welcome back guys. So in continuation of our discussion on sampling distribution, last class in my last lecture, if you remember, we discussed chi-square distribution and just we ran short of time in discussing a problem related to chi-square distribution. First I'll start with that and then I'll go to t distribution. Okay. So I think you guys can remember what is chi-square distribution. Chi-square distribution we use for sampling distribution of variance, like sampling distribution of mean, we have sampling distribution of variance. Sampling distribution of variance, why it is used? We use to infer, if we have to infer something about the population variances. Usually it is mostly used in food and beverages industry, where quality is very much a paramount importance. And then we need to find out how much variant is it from the specified volume or the specified weight. In those cases, we need to find out the infer the volume of the, the variance of the volume. For that, we need sampling distribution of the variance, and for sampling distribution of the variance, we use chi-square distribution. So we have discussed what is chi-square distribution in my last class. So today we'll be solving one problem. Of course, I'll be solving some other problem in my tutorial classes also, this problem, so that you can understand the topic better basically. So now what is the question here? A manufacturer of a car batteries guarantees that a battery will last on average 3 years with a standard deviation of 1 year. Okay. So manufacturer, it guarantees that on an average the battery will last 3 years with a standard deviation of 1 year. Okay. That is the manufacturer's his claim. So now if 5 of these batteries have lifetime of 1.9, 2.04, 3.0, 3.5 and 4.2 years. So what happened? A person, he bought this battery, or rather might be you can take it in this way, like he wanted to do a bulk purchase of batteries. Before that he might want to check it whether what the manufacturer is claiming is correct or not. Maybe that's the reason, or maybe he has bought it for his own need and he found that this lifetime of this battery is this 1.9, 2.4, 3.0, 3.5 and 4.2 years. Should the manufacturer still be convinced that the batteries have a standard deviation of 1 year? Okay. So with this, we are not interested in finding the average lifetime. Just what we are interested, should the manufacturer still be convinced that the batteries have a standard deviation of 1 year? That means the variance among them, if the variance among them is 1 year or not, that is the manufacturer, whatever he is claiming, is it correct? Okay. That's what he wants to find out. So remember while discussing chi-square distribution, we have seen that, okay, let me take this. Chi-square distribution is something of some skewed sort of distribution, remember? So it was something, this portion, it's both the portion is same, but my figure is not very good. So it is like 0.9975 and this is 0.025. This area is 0.025 and this whole area is 0.975. So if the probability lies in this range, yesterday we have discussed, then it is then whatever is our claim is correct. That's what that's a reasonable values of probability basically. If it lies within this range, that's a reasonable values of probability. We have seen yesterday in last class basically, if the probability lies in this range, which is a very less probability, under what situation the probability will lie in this range? Remember what was the chi-square value? Chi-square value is n minus 1 s square by sigma square. Probability will lie in this range when chi-square value is quite high. Under what situation chi-square values will be quite high? When this value will be very less. When sigma square value is very less, then we will get a very high chi-square value. This sigma square value, that's a variance value, a very less variance value, that is very much unlikely. It is not that it cannot be, but it is very much unlikely that it will have a very less chi-square value. At the same time, we will have a chi-square value, a very lesser chi-square value if we have something in this region. A chi-square value will be very less, isn't it? Because it is starting from 0. So under what situation we will have when chi-square value is, when sigma square is very large. So that is also quite unlikely. Why? When the sigma square is very large, that means the process is not stable. When the process is not stable, why at all will go for doing this statistical inference, isn't it? It is an unstable process. So it is that's the reason the value lying in this range is very, very unlikely. But it is not that it may not happen, it may happen. But if it happens in this range, if my probability lies in this range, then it is okay, and this is the claim is correct. So now essentially this problem we need to find out whether our probability lies in that acceptable range or not. Okay, so how do we solve this question? First is that we need to find out the chi-square value. For chi-square value we need to find out the S square, that is the variance of the sample. So variance of the sample, this is variance, you know the formula for variance, or we can use one more, there is one more formula for variance which let me give you, there is one more formula for variance, like it is 1 by n into n minus 1, this is n, n into n minus 1, then sum n into summation of I is equals to 1 to n yi square minus I is equals to 1 to n yi, oh sorry, it is not yi, always a xi, xi whole square. Okay, so this is also one formula for, let me rub it, okay, and so this is also one way of calculating variance. Variance formula, I think you know the one, the standard formula which you know, you can calculate it using that formula also, or you can calculate it using this formula also. Here I have used the other formula which I have just now written. So we calculate the variance from the sample. Sample variance I already told you, we specify it by S square. So we found S square, sigma square is given, we know what is n is 5, so it is n minus 1. So we found a chi-square value. Chi-square value we got is 3.26. Now we need to find out for what is the degree of freedom here. Degree of freedom is n minus 1, that is 4. So we need to find out for 4 degrees of freedom what is the acceptable range. That we will, for that we will consult the chi-square table. So I told you we have a chi-square table so as to consult the value. So basically this is, you see, this is the chi-square table, and chi-square table, you see, for 4 degrees of freedom, this is the area corresponding to this is the value of chi-square corresponding to value of area of 0.975. So this maybe this area, this area, if this area is 0.975, this value is 0.484. This is for degree of freedom 4. Okay, and then it is 0.025, maybe this region 0.025, this the value of this may be 11.143. So if my value lies between this and this, then it is acceptable. Okay, so what value I got? Definitely it lies within this range. Okay, so what value I got? I got 3.26, chi-square value 3.26. So 3.26 lies very much within this range, within this 4.484 to 11.413, it lies within this range. Okay, so that's why, since here I have written it, since 95% of the chi-square values with 4 degrees of freedom fall between 0.484 and 11.143, the computed value with sigma square is equal to 1 is reasonable. It is a reasonable value because it falls within an acceptable region, that is, it falls within a 95% of the values, right? And therefore the manufacturer has no reason to suspect that the standard deviation is other than 1 year. So what the manufacturer claim is, we can say that it is correct. He has no reason to suspect that. But always all these things, when you talk about probability, always all these things is a probability concept. Probability means the uncertainty is already always there. It is not a definitive answer. Okay. So that is the chi-square distribution. Now coming to t distribution. Okay, like chi-square distribution we use for sampling distribution of variance. We have seen for sampling distribution of mean, we have seen that we use Z distribution, right? So So for sampling distribution of mean, we also use t distribution. Now, under what situation we use t distribution, that we'll see. First, you see, when we have used sampling distribution of mean, when we have used z distribution, see, this was our value. This is the value where we use to find out the z value. Z is x bar. What is x bar? Is the mean that we get from the sample. X bar minus mu sigma by root n. Here you see, when we compute z, and while explaining sampling distribution of mean, I have told again and again, this mu value, what is our objective from sampling distribution of mean? Our objective is to infer about the population mean, right? So you may think we have to infer about the population mean, then we already have mu, then what we have to infer? It is already given. No, it is not given. It is I told you, it is estimated. It is, or I can say it is an educated guess. It may be the producer or manufacturer or whoever the person may be. He is just claiming. From the sample, we have to find out whether what he is claiming is true or not. We have just taken it as a estimated value or predicted value. Now the question is, when we don't know the mean of the populations, having an idea about the variance of the population is very, very remote. We don't know the mean only, how can we know the variance of the population, isn't it? If the population is something very known population or from the past experience, then we can say variance of the population may be so and so. But usually in most of the cases, when mean is not known, having a knowledge about the variance is difficult. In such cases, when we don't know the variance of the population, mu2, okay, we have guessed it or we have predicted it, that we will find it out using the sampling distribution of the mean. Whatever we have predicted is true or not, that will find it out, fine. But the variance what we have predicted, that is usually, it is very remote that you can predict the variance. Okay. In this case, when you don't know the variance, we cannot use z distribution, because z distribution, the formula directly says that we need a sigma here, directly says. So how can we use z distribution? So instead of sigma, we will need to use s, that is the standard deviation of the sample, or rather we will have to use the variance of the sample. So when we use, instead of sigma, when we use s, then it becomes then we can no longer, it no longer fits to a normal distribution. So the distribution that we use here is the t distribution. Okay. So that's what. So whatever I told here, this required a known values of sigma a priori. However, in many situations, knowledge of sigma is certainly no more reasonable than the knowledge of the population mean mu, right? So in such situation, only measures of the standard deviation available may be the sample standard deviation s. So if we substitute sigma by s, the problem is that the resulting statistics. So what is the statistics now? The sample statistic is the t value, right? So sample statistic is now not normally distributed. Earlier my sample statistic was z value for sampling distribution of mean, that was normally distributed. In sampling distribution of variance, my sample statistics was the chi-square value. So that chi-square value was chi-square distributed. So now this distributed, empirically it is found that it fits a distribution which is called a t distribution. It is called student's t distribution, or simply we can say it is t distribution. Okay. Now what is t distribution? Any distribution means we need to know its PDF, probability distribution function. If it is continuous, then probability density function, whatever it is, we need to know that, right? So t distribution, this is the PDF of t distribution. Here also there is only one parameter, that is the degrees of freedom. Okay, t distribution with v degrees of freedom, it takes z by chi-square with v degrees of freedom divided by the degrees of freedom. That is the PDF of t distribution. If you just Google t distribution, you may find a different expression, but one simplified form. This is a simplified form of t distribution. Similarly, if you Google chi-square distribution, you may find a different form. Whatever form I have given, that's again a simplified form. Different simplification, different way of simplifying, because chi-square we use in different application. In different application, we will use its different representations. Okay. So similarly, t distribution we will be using this representation. So what is this? Z by square root of chi-square with V degrees of freedom divided by V degrees of freedom. Now we know what is Z value, we know what is chi-square with V degrees of freedom, what is that. If we substitute this, then maybe we will get it whatever we need. We need something in terms of sample parameter, sample statistics, okay. For in case of sample, I should never talk as parameter. Parameter is always for population. So now see here, now using here. So we have Z is equals to this, chi-square is this, we have seen chi-square is this, we have seen Z is equals to this, and from the sample, if x1, x2 are the independent random variable and with mean, mu and standard deviation, then I can find x bar is this way and s square is this, that is the sample variance. This already I know. So now in this t distribution formula, if I substitute the value of z and chi-square, what do I get? I am replacing this z by chi-square value as just a simplification. Upon simplification, I will get this is my, this is the PDF takes this form, x bar minus mu s by root over n. S is the sample variance. Now I don't need to know the population variance. Even if I don't know population variance, I can still make a guess on the, I can still make an inference on the population mean. But of course, I'll have to first take an educated guess, or I have to take some estimated value of the population mean, or I have to predict some population mean. So this is the thing. So this is the statistics. This t value is the statistics that we'll have to find out from the sample. Given a sample, I'll have to find this t value. What is, how do I find the t value? T value is x bar minus mu by s by root over n, and then accordingly now the way we do for z distribution, the way we do for chi distribution, chi-square distribution, similarly for t distribution, we have also lookup table. From the lookup table, we can get the value. But here t distribution is also one of the characteristics of t distribution. This distribution also very much symmetric like a normal distribution. So since it is symmetric, so on the table we have only the values for the upper tail, but the right tail. The lower tail values are not given in the distribution, because if we know the right tail values, we can go get the values for the left tail as well, because this is symmetric, isn't it? Like for z distribution, the whatever value we get for z is equals to -2, the same value we will be getting for z is equals to +2, isn't it? So because it is symmetric. Similarly for t also, so that's why in fact in z we have seen we have given values for all the upper tail and the lower tail, but t distribution in the table only, in most of the table only the upper tail is given, but we can definitely find it out from the lower, from the upper tail we can find out the lower tail. Okay, so now t distribution, okay, t distribution, some more characteristics of t distribution. T distribution is like, if I draw the formula figure for t distribution, like it is very much similar to normal distribution, but it has a fatter tail. This tail portion is fatter compared to the normal distribution. Fatter means probability, here the probability of occurrence of random variable is quite more compared to the normal distribution. Okay. And one more thing, when my sample size is big, then this difference does not make this. If I take whether I am taking s square or whether I am taking sigma square, the difference doesn't have a much impact, and that's why for greater sample size, instead of t distribution, I can very well use the normal distribution. The result will not be unreliable. It will be with precision estimate. It will be with good precision only. Instead of t distribution, I can very well use the normal distribution for a bigger sample size. So now the question: a chemical engineer claims that a population mean yield of a certain batch is 500 grams per milliliter of raw material. From per milliliter, there are some raw materials are there. From that, the mean yield of the population mean yield will be, it is 500 grams. Okay, he claims that. To check his claim, this person, he is suspicious of his own claim, so he wants to check it. Whatever he is done, to check his claim, he samples 25 batches each month. That means his sample size is 25 now. If the computed t value falls between this minus 0.0 t of minus 0.05 to t of 0.05, he is satisfied with this claim. Okay. What conclusion should he draw from the sample that has a mean of x bar is equals to 518 grams per milliliter and a sample standard deviation of s is equals to 40 grams. See here, population standard deviation he doesn't know. He is just having a guess of mean means he is guessing that it is around 500 grams, okay, but he himself is not convinced, so he wants to check. For checking what he has done, he has taken a sample of 25, a batch of 25, that is his sample size, and from there, since he has to infer on the population mean. So it will be sampling distribution of mean. Now sampling distribution of mean we have learned two. We can either use Z distribution, we can use T distribution. Now here we cannot use Z distribution because we don't know the population standard deviation. So we will have to use T distribution because we don't know the population standard deviation, and we here we have the sample standard. Sample standard deviation, definitely if it is not there also given the data, we will be able to collect the sample standard deviation. So he will calculate the T value. Now what he is claiming that if the computed T value falls within this range means what? T of, let me draw the figure, it will be something. Okay, so this is, I am very bad in drawing actually. Okay, so it goes this way it goes, okay. So he is satisfied with this claim if it falls in T of minus 0.05 means minus 0.05 means this portion plus 0.05 means this portion. So he is satisfied if it falls within this range. That is quite reasonable, right? That means if it is falling within this range means probability of occurrence is quite high. Means if this is true, probability that I will be getting this 518 value, it's a high probability because this is very less probability, isn't it? That's what. That's his whatever experiment he is taking, quite justifiable experiment, because if this is true, then from the sample what he is getting, probability of occurrence of that should be, it should have a higher probability. If it has a very remote probability, that means what he is claiming is not true. So that's why he has taken this range. Now let's see how he has done it. So we have seen from the T table, as I told you, in the T table only the upper tail values are given, lower tail values are not given. So in the T table, and one more difference, like in Z distribution, as I told you, we get the CDF, cumulative distribution, from minus infinity to x, but chi-square is different. Chi-square we get the value, the right side of the value. In fact, 1 minus of the CDF, that's why we get in chi-square. Similarly in T distribution, alpha value is the area, this is the area. Rather than this portion, we have this portion in the table. So that's the difference. The T value and chi-square is same, we have the right side value. So here what is the, how many degree of freedom? Degree of freedom is 24 because there is 25, sample size is 25. For 24 degrees of freedom, for 0.05, what is the value? 1.711. For 24 degrees of freedom, T05 is this value corresponding to this is 1.711. Okay. So what will be the value corresponding to minus T of 0.5? It will be, because it is symmetric, it will be minus 1.711. This minus value is, lower tail values are not given, but it is symmetric. So I can, if I know that, I will be able to note this, isn't it? So if it falls, if my calculated T value falls within this region, calculated T value falls within minus 1.711 to plus 1.711, that means this is whatever his claim is justifiable. Okay. So what did he get? So he calculated his T value. This is how he calculated his T value. Okay, using the T value formula. What is the formula for the T? Remember, x bar minus mu s by root n. This is the formula for the T value. So he calculated the T statistics. T statistics from the sample he got 518. This is the he has predicted this population mean 500. Okay. Then sample standard deviation 40 divided by root n, that is 25, and what we got is 2.25. 2.25 means if I draw the figure, if I draw the figure, if this portion is say 1.711 and then he got it somewhere here, that is 2.25, somewhere this portion. This is minus 1.711. He did not get within this. He got the value, what he got is beyond this. That means probability of that occurrence is very less. It's a very remote probability. That means whatever he is claiming that the mean yield mean is 500 gram, that is not true. If that is true, we from the sample, because sample is something which we have tested it cannot be wrong. It is, we have collected it and tested it. It cannot be wrong. It is giving us the true picture. So if that is true, then this should have been true. But what I got, this is from this, taking that is true, I got a very less probability. That means what I have assumed, what I have estimated the population mean 500, that is not correct. Okay. So now you can see if that is not correct. So what may be the probable values of 500? You see, I got a value 2.25. If I would have got a lesser value than 1.711, lesser than, under what situation I will get? If this 500 would have been, if this is instead of 500, if this value would have been more, then I would have got a lesser value, isn't it? So first thing, the probability of getting a t value greater than 2.25 for this is approximately 0.02, very remote probability. That is my first observation. Second observation, mu is greater than 500, the value of t from the sample is no more reasonable. Third, hence the engineer is likely to conclude that the process produces a better product than he thought. Actually, he was very pessimistic instead of optimistic. He was telling that my thing mean yield is 500, but he didn't know that his process yield is much more than that. That's if he would have predicted his process yield is much more than 500, then his value would have been within this range. Okay, so that's all in this lecture. So we have till now we have learned chi-square distribution, we have learned t distribution, and there are few more sampling distribution which we'll be learning in my next lecture. Okay, then these are the references. Okay guys, thank you.